Hi everyone, this is Dr. Matsuko with a micro lecture on the relativistic Doppler shift. But before I get into physics, my son Luke wants to say hi.
Hi.
There you are. That's hi from Luke. All right, so here is a micro lecture on the relativistic Doppler shift. It's very, very similar to the Doppler shift for sound, but this is Doppler shift for light. Right? And so the equation is slightly different, but what we see is that the wavelength, we're going to call lambda naught our proper wavelength, and then the observed wavelengths are different. Observed, and they depend, or that difference, how they're related to each other, depends on this big square root crazy thing, which likewise depends on beta, which is V divided by C. Right? So V is going to be the speed of the source. Right? So we got two pictures here. So I need to put a better line there. Right? So if you imagine that you're just standing somewhere, and then there's some kind of source like the sun, and it's emitting some green light or blue light or whatever, and then whatever wavelength is coming out of the sun is the same wavelength that you're going to observe. All right? Or you could put observe. Some people put a prime on there. Various things like that. But imagine that the sun is actually moving, and that you are still standing over here on the side. Right, so the sun is putting out maybe still green light, but as it's moving towards you, right, direction of motion, as it's moving towards you, then that means the wavelength gets squished, and so your observed wavelength is going to be smaller than the actual wavelength. If instead you are behind the star, and then the star's going away from you, right, then your observed wavelength is going to be greater than the actual wavelength that the star is making. You can probably hear my son is pulling out his coloring book, which is cool. All right, you can do your coloring book. All right, so let's see, observers in front, or observers where they're getting closer together, experience a blue shift, whereas observers that are behind or where they're separating have a red shift. Right? And so I put that up here. I covered all of it again. And note that V, the speed, is positive for increasing separation. And if separation is increasing, if the source is moving away from you, then you're going to get a red shift. You're going to get a longer wavelength. So that's the overall overview of relativistic Doppler shift. Let's do some equations or some calculations. All right, so first, a spaceship, let's see, speeds away. That's my beautiful spaceship. And it's going at a V equals 0.25 C. Oh, it's going away from a timing station. I have no idea how to draw a timing station. Let's build a house like that. All right, so there's a station, and we have a spaceship that's moving away from it at V equals 0.25 C. And then, let's see, a source on the rear of the ship emits light at a wavelength of 555 nanometers, according to someone on the ship. All right, let's see if I can change colors here. 550 is roughly green light. Right, so you have some lambda naught equals 555 nanometers. And it's going like that direction. What wavelength is detected by someone on the timing station? Right, so what wavelength will they see? Well, we can already know they're moving away from each other. I'll go back to blue, right? They're moving away from each other. And so that means it's going to be redshift. Which means that lambda will be greater than lambda naught. Okay, so that's something I know conceptually, and I'm going to use that to double check to make sure I got my negative signs and positive signs correct. All right, so let's use our equation. Lambda equals lambda naught square root 1 plus beta and 1 minus beta. All right, so we have here beta equals V over C. And let's see, V equals 0.25 C divided by C. And so we get beta equals 0.25. All right, so our lambda equals, let's see, lambda naught is 550 times 10 to the minus 9 times the square root of 1 plus 0.25 divided by 1 minus 0.25. Lambda equals 550 times 10 to the minus 9 square root of 1.25 divided by 0.75, and I get lambda equals, I'm going to type this into Google, 550 times 10 to the minus 9 times the square root of 1.25 divided by 0.75, and you press go, and I got 710 times 10 to the minus 9 meters. Let's see. So I already said to double check. I'm going to make sure that it is redshifted. So lambda should be greater than lambda naught, and it is. Awesome. All right. So that's one example. All right. Let's do another example. Okay, one of the calcium absorption lines in the Hydra galaxy spectra appears shifted from 394 nanometers to 475 nanometers. Right, determine the velocity of the Hydra galaxy relative to us. Right, so that's saying it's shifted from means that's the lambda naught. Lambda naught equals 394 nanometers, and 2, that means lambda equals 475 nanometers, and we want to determine V. Up here shifted. Well, we know that lambda is greater than lambda naught, right? That's what we're seeing. 475 is greater than 394, so that's a redshift. So that means they're moving away. All right. Which increasing separation means we have a positive V. V is greater than 0. All right, so I know that, so already we can know that this Hydra galaxy is moving away from us. Yeah, relative to us, right? And so we can actually calculate what that is, right? We get our equation again, lambda equals lambda naught root 1 plus beta over 1 minus beta. Right. There's actually a lot of algebra that goes into this when you're trying to get rid of it. So lambda over lambda naught squared equals 1 plus beta, 1 minus beta. And at this point, I actually find it easiest to do this numerically rather than to actually solve for beta. So first let's do lambda. Let's see, 475 divided by 394 squared, and that equals how's it going, Luke? Good. Awesome. Okay, 475 divided by 394 squared, and we get 1.45. Right, so 1.45 equals 1 plus beta and 1 minus beta. So I'm just gonna plug this in and guess numerically. This is actually what numerical means. So let's do 0.2. Well, let's do 0.5. Okay. 1 minus 0.5. All right. So if beta equaled 0.5, that means that we would get 3. All right, 3 would be lambda naught over lambda squared. And so that's not right. That's too big, right? I'm looking for 1.45. So let's do half of that. Okay, instead I'll do 1 plus 0.25. And actually, I think that's what we did last time, right? 1 plus 0.25 and over 1 minus 0.25. And that's a 1.67. Right, so I'm getting closer to the 1.45. So I'll do a little bit smaller. Let's do 0.2. Let's see. If beta equals 0.2, I get 1.5. That's really close. Let's see. Let's do 1.19. 0.19. Oh, 1.47. Okay, what happens if I do 0.18? Okay, for 0.18, I get 1.44. So it's somewhere around there. I'll give it one more guess, and I think it'll be close enough for Wiley plus to approve. All right, for 0.182, 1.445. Okay, I'm going to do 3. I said I would only do one more guess, but now I really want to get close, right? I think I'm going to have to do 0.185. Okay, 0.185. Let's see, if beta equals 0.185, I get 1.454. And so it's somewhere around there. All right, V is approximately equal to 0.185 times C. All right, because beta, right, V equals beta times C, and I don't know why there's a second one right there, right? So I don't know, in my experience, this is the fastest way to really figure out the speed or this beta, because actually algebraically solving for this beta is annoying. Right, so I'm going to leave it there. All right, so we have our velocity of the Hydra galaxy relative to us is going to be positive, and it's roughly 0.185 c. Right, so that's fast, a fifth of the speed of light, but it's going away from us. Here, actually, is a picture. This is not the Hydra galaxy, but this is a different galaxy. It's a super cluster of galaxies called BAS 11, and this is actually showing the absorption lines. So here I specifically chose the 394 nanometer line. 394 is probably over here-ish, maybe. 394 is usually blue. Right, yeah, is blue. And so we can see that, especially this, whether or not that's the 394, this is a pair of lines, and we can see that that shifts over, right? And so pretty much all of these lines have shifted over, and that's pretty cool, I think. You think it's cool, Luke?
It's so cool.
It's so cool, thank you. Yeah, it's pretty cool that actually for almost every single star and galaxy that we've looked at, almost all of them are redshifted relative to what we would expect based on what we know about hydrogen and calcium, which means that basically all of these stars are moving away from us. Not every single one, but almost all of them are moving away from us. And so when we start talking about cosmology and the Big Bang, we're going to come back to this. And this is actually one of the experimental proofs of why most scientists believe in the Big Bang theory. And there we go. That's it. So I hope this was helpful for you guys, covering the relativistic Doppler shift. And I'll see you guys again soon.